My name is Thomas Ebel, and I am Professor for Advanced Capacitor Technologies and Head of the Center for Industrial Electronics at the University of Southern Denmark in Sønderborg, close to the German border. Me and my team are working on new capacitor technologies for the next generation power electronic devices. In this presentation, I will talk about advanced capacitor technology, especially about the challenges for capacitors related to applications with wide bandgap semiconductors. This slide with a chart from Infineon shows an overview of the application areas of silicon, silicon carbide and gallium nitride. Here the power level of the application is plotted versus the frequency. It is common understanding that the new wide bandgap devices, silicon carbide and gallium nitride, are used in different power frequency areas. Silicon carbide is actually more suited for higher power levels and lower frequencies, whereas gallium nitride is more used for lower power levels and even higher switching frequencies. What does it all mean now for the use of capacitors in the so-called wide bandgap DC link applications? The capacitors will be operated at higher switching frequencies. Therefore, the ESR of the capacitor must be as low as possible in the relevant frequency spectrum. The parasitic inductances must be as low as possible, because with increasing switching frequencies also the losses will increase. To reduce the parasitics, it is needed to connect the capacitors very close to the hot switching devices. That means that the temperature stability of the used capacitor materials must be as high as possible, or using sophisticated cooling, active cooling means. Last not least, the miniaturization trend of the wide bandgap devices demands also an ongoing miniaturization trend for the passives and therefore, of course, for the capacitors. First, I will talk about aluminium electrolytic capacitor technology. This scheme shows the principal construction of an aluminium electrolytic capacitor. It consists of a winding element of so-called anode-cathode foils separated by paper. The electrodes are connected by taps or pedal taps to the outer world. The winding element is impregnated with electrolyte and later sealed in an aluminium housing with a deck. This slide shows the core material of a high voltage aluminium electrolytic capacitor, the anode foil. Here you can see the SCM cross-section of a circa 120 micron thick anode foil. One can see the etching structure composed of several million so-called tunnels etched perpendicular into the surface. This etching structure is responsible for the high capacitance of a high voltage aluminium electrolytic capacitor. This slide shows the etching structure of an anode foil. It was prepared with a gallium focus ion beam machine in an SNM. One can see the uneven tunnel distribution of the etching structure around the residual aluminium. To produce an aluminium electrolytic capacitor, the aluminium surface must be anodized. This slide shows the complex oxide structure inside the etched tunnel structure of an anode foil. The oxide is the capacitor dielectric. Now I will talk about new concepts of capacitor technologies of aluminium electrolytic capacitors. Conducting polymers like P.PSS types are good candidates for improving the ESR of aluminium electrolytic capacitors. because they have a 10 to 100 times higher conductivity than liquid electrolytes. This slide shows the thermographic analysis of a P.PSS sample. P.PSS is principally very temperature stable. It decomposes far over 300 degrees and is a good candidate for high temperature aluminium electrolytic capacitors. In our research, we are using P.PSS formulations for high voltage capacitors over 400 volt. This photo shows the impregnation of a tunnel structure of an anode foil with P.PSS. This slide shows the ESR frequency behavior of a high voltage capacitor sample impregnated with standard liquid electrolyte versus a sample impregnated with P.PSS electrolyte, measured in the range between 20 and 100 kHz. One can see that the ESR is factor 10 lower with P.PSS at higher kilohertz frequencies. This slide shows the breakdown voltage behavior of a P.PSS impregnated capacitor sample, measured at 150 degrees Celsius. One can see that a breakdown voltage of 572 volt was obtained. So the target producing a 450 volt capacitor seems to be possible. This slide shows a prototype of a multi-stacked aluminium electrolytic capacitor with this technology, having a capacitance of circa 70 microfarad and an ESR of 50 milliohm at 450 volts, supporting ripple currents of at least 20 amps at 10 kHz and up. Now I would like to talk about our work in the fields of metallized film capacitors and power capacitors. This slide shows the basic construction of metallized film capacitors. Normally two thin polymer films with a thin metallization layer on top are wound up, and the top and the bottom of the winding element are metal sprayed to interconnect the plus and minus electrodes respectively, having free edges to have separate metallization and interconnection. On the left hand side one can see the SEM photo of a metallized surface film. This table shows different polymer materials used for metallized film capacitors. The main difference is related to the operation of the polymers at different application temperatures. Now I will talk about our research on new concepts for capacitor technologies used for metallized film and power capacitors. We work with nanocomposites to improve the dielectrical properties. We use barium titanate for increasing the dielectric constant, silicon dioxide for increasing the breakdown strength, and bore nitride to improve the thermal properties of the polymers. It is well known that the addition of nanoparticles lead to clustering of those particles due to the high surface energy, and the aimed properties were negatively influenced. SDU has developed a new technique to avoid this clustering effect by embedding the nanoparticles in a chemical environment, which leads under special process condition to a very homogeneous distribution of the nanoparticles, and that means that the properties are really positively influenced. We could demonstrate that with an addition of only 0.7 volume percent of barium titanate, we could increase the capacitance, especially the electrical constant, of the capacitor by 20%. This gives us a possibility to dramatically and heavily improve the capacitance of for example, high voltage capacitors and reduce the overall size of it significantly. I would like to summarize my talk. SDU is working on next generation capacitor technologies. P.PSS high voltage polymer electrolytes based aluminium electrolytic capacitors could be the solution for wide bandgap power devices having low ESR and high temperature stabilities. Nanocomposite polymer dielectrics could be engineered to have the right capacitance, thermal stability, and high breakdown strength. More to come. Thank you very much for your attention.